Hi everybody, my name is Sean O'Kane with ChipEstimate TV and ChipEstimate.com, where we bring you the latest trends and information in semiconductor design and IP. My guest today is Dr. Gary Patton, Vice President, Semiconductor R&D Center with IBM. Thank you very much for joining us. Dr. John Heinlein, Vice President of Marketing, Physical IP Division with ARM, and Vasilios Gerosis, excuse me, is the Distinguished Engineer with Cadence. Again, thanks for your time. Gary, we all know the collaboration is very important in this industry, even more so, especially with this 14 nanometer tape out. And you've demonstrated that collaboration with the 14 nanometer FinFET. Can you tell us a little bit about this technology and the advantages of this advanced process node?
First, I do want to emphasize how valuable, how important this collaboration has been with both Cadence and ARM. There are many new subtleties in the design which come in with double patterning, with the FinFET device structure, and being able to look at a variety of different libraries and how to optimize them to really get the maximum benefit was very, very important.
Right.
And then to get this product IP out onto our test site so we can start to get hardware validation on it. Mm-hmm. Now for FinFETs, there are some significant challenges, and there's been a number of articles in the various journals about the challenges of a bulk FinFET, for example. Fin height control, fin profile shape, junction isolation, parasitics associated with that. All of those detract from the benefits of the FinFET device structure. Mm-hmm. By going to SOI, we basically eliminate all those issues. Fin height control is determined by the silicon cap on the oxide, very easily controlled. Since you got oxide underneath, there is no junction isolation, and we were able to get very good vertical profiles because we don't have to etch as deep. Mm-hmm. So we see some very significant advantages.
That's important because, and with this collaboration and ARM being very strategic with this tape out, John, talk about a little bit of the design, designing the standard cell technology.
Sure. We've been collaborating with IBM for many generations now, and ARM is the leader in logic IP development, and we've worked very early for 3 or 4 generations now on this kind of early test chip engagement. We'll talk more about the test chip later on perhaps, but one of the things we look for in the early test chip is looking at the kind of fundamental structures we want to pattern that make effective, scalable, high-performance standard cells. Obviously with the addition of double patterning, there are new issues that come up in terms of how we draw the cells, making sure we structure the cells and the cell architecture, as we call it, appropriately. And on this test chip, not only do we implement the test chip, but we also have a number of test structures that allow us to look forward to choices we might make in production libraries that we'll be developing now.
Vasilios, in regards to the FinFET methodology, what is the perspective on a tool development?
So for the FinFET technology, it affects more on the custom transistor level side. So people have to deal with the number of fins versus the width of the transistor, which is usually is not which is discrete, and the simulation part of it as well as parasitics. So it complicates the transistor level design. But from the digital side, is similar to what we've done in 20 nanometer with double patterning technology.
Yep. I was just going to mention that because Gary mentioned the double patterning, and with all the work done at 20 nanometer, how does that fit in with 14?
So with the 14, luckily many of the rules that were done with 14 is similar to 20, similar to what we've done in 14. Right. So it was easy to move into the 14 nanometer environment. So from a tool perspective, we had to add few rules to make the tape out, but that's primarily the main challenge that we had on the digital side.
John, why was the Cortex M0 chosen for this test case or test chip?
Sure, we've established a methodology for several generations now where we've used in this very early generation the Cortex M0 as part of our test structure. And you know, this was the first test chip we've done on FinFET, the first test chip we've done on 14 nanometer. And we use M0, which is a very well-known quantity. It's more well-controlled because it doesn't have as much of a cache infrastructure as more advanced cores do. So we have that as the foundation of our methodology. And on the side, we put many different experimentation structures to look at different logic configurations. So that, coupled with the Cortex M0, then allows us to plan for the libraries we come in the future. Now, what's interesting about this test chip in general is we really see it as planting the seeds of the production designs that will come several years from now. We talked about today at the forum how the Cortex M0 equivalent chip we did in 2008 is now in production in 32 nanometer designs today that you can buy in the stores. So what we're doing is investing in designs that are going to come a few years from now and helping de-risk those designs.
Excellent. Did anybody want to talk a little bit about the low power techniques that is associated with FinFET?
It's big to know the technology, Gary. Do you want to talk about that a little bit?
Well, from a technology perspective, you know, it's about optimizing for low leakage.
Right.
As I said, with SOI, we don't have the issues of junction substrate leakage. So it gives some inherent advantages with that particular structure.
One of the things we're looking for, of course, as we go into FinFET is better ion-IOF characteristics and also the ability to drive minimum operating voltage down lower. Today, minimum operating voltage has hit a bit of a wall, and we're trying to continue to scale it down to help drive standby power and power efficiency. So those are the potential promise of FinFET that we're hoping to gain as we move to this technology.
Gary, any other exciting tape outs that you have?
Well, we have the hardware running in the line with the existing set of IP, and we'll be working very closely with John and the rest of the ARM team to really understand how to co-optimize the design and the technology to get the maximum benefit out of it. And then from that, we'll be taping out, you know, more extensive product IP later this year.
That's great. I thank you for your time. I really appreciate that. Dr. Gary Patton, John Heinlein with ARM, and Vasilios Gerosis with Cadence. Thank you very much.
Thank you.
And for these gentlemen, my name is Sean O'Kane with Chip Estimate TV. Thank you very much.